Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we focus on one essential component of the epistemic firewall. In this part 37, we deploy the firewall's most subtle and crucial diagnostic instrument. We define the grammar pathology detector system. This is the firewall mechanism that exposes rules which work perfectly. They feed the data, make successful predictions, pass initial checks, but for the wrong reasons. They are not constraints on phi, they are artifacts of hidden, non-physical constraints smuggled into the data processing pipeline. The core revelation is a deeper layer of skepticism. A pathology detector is a failure mode library, diagnostics for rules that succeed due to coincidence, leakage, sampling bias, or hidden coupling. Passing predictions is not enough. We must verify why predictions succeed. The skill you will gain is that of a pathology hunter. You will learn to interrogate not just if a rule works, but how it works, to dissect its success and see if it depends on artificial, pre-injected structure. Our core question is precise. How can a rule work, yet still be wrong? This question targets the most sophisticated and dangerous form of false positive. A rule can pass the metagates, survive negative controls, and even make accurate predictions, yet still be a pathological fit. Its success is not due to capturing a true constraint of phi, but due to exploiting a hidden regularity imposed by our own methods. The rule is a parasite on the pre-processing pipeline. It works because the pipeline, often unintentionally, guarantees the very pattern the rule claims to discover. The pathology detector system is a library of tests designed to find these hidden guarantees and break them. Why is this detection necessary? The failure mode it prevents is the institutionalization of methodological artifacts as laws. A pathological rule can become the foundation of a research field, guiding experiments and theory for decades, only for its entire edifice to eventually collapse when someone finally notices it was built on a software bug, a sampling quirk, or non-physical smoothing assumption. The detector protects against this long-term costly error by forcing us to validate the mechanism of success, not just its occurrence. In holophase terms, the pathology is a disconnect between the rule's claimed constraint and the actual source of regularity in the data. The rule G claims to describe a relationship between derivatives of phi, but the observed regularity might come from a step before phi is even properly observed, from the windowing, filtering, discretization, or noise model. The pathology detector forces us to audit the pipeline for hidden constraints that could masquerade as phi's laws. In the triunity, common pathologies have distinct signatures. 1. Omega pathology, temporal artifact. The rule fits temporal patterns well because the timing structure was implicitly constrained by pre-processing. For example, if you apply a strong low-pass filter to noisy time series data, you artificially create smooth, slow oscillations. A rule that discovers these specific low-frequency oscillations is not discovering phi's rhythm. It is reading the filter's cutoff frequency. The pathology signature. The rule's characteristic omega vanishes if you change the filter bandwidth. 2. K-pathology, spatial artifact. The rule's spatial invariance holds because the discretization, or grid, bakes in smoothness or symmetry. For example, if you represent a continuous field on a regular Cartesian grid with a specific interpolation scheme, you impose an artificial anisotropy, directions aligned with the grid. A rule that discovers alignment along grid axes is reading the grid, not phi's geometry. The pathology signature. The rule's K-pattern changes if you rotate the coordinate system or use an unstructured mesh. 3. V-pathology, dynamical artifact. The rule's motion coupling appears coherent because frame assumptions were hard-coded into the analysis. For example, if you analyze planetary motion, assuming a perfectly inertial solar system barycenter frame, and your rule discovers a force law, it might be secretly dependent on that specific frame choice. A real force law should be covariant, take the same form in any inertial frame. The pathology signature. The rule's V coupling changes if you boost to a different inertial frame. The detector works by proposing and testing alternative, non-physical explanations for the rule's success. It asks, could this success be explained by a known artifact of the pipeline? It then varies the pipeline element suspected of causing the artifact and observes if the rule's success disappears. This connects decisively to energy esteli. Pathological rules often produce beautifully balanced energy accounts, but they do so by smuggling bookkeeping through pre-processing. For instance, a common pathology in fluid simulations is artificial numerical viscosity. This is a damping term, an energy sink, introduced by the discretization scheme, not by real physics. A rule that discovers a certain viscous dissipation rate might just be measuring this numerical artifact. Its energy tally balances because the numerical scheme itself conserves a modified form of energy. The pathology detector would vary the spatial resolution, the K discretization. If the dissipation rate changes with grid size, it's a numerical pathology, not a physical law. The operational interpretation is found in the practices of convergence testing in computational physics and sensitivity analysis in complex statistical models. Before trusting a simulation's result, you must show it is grid independent, that the inferred rule doesn't change as you make the mesh finer, testing K-pathology. Before trusting a machine learning model's feature importance, you must show it is robust to different data splitting seeds, testing a form of omega pathology from random sampling. The firewall role, therefore, is that of the pathology auditor. When a rule G presents itself with apparent success, the auditor consults the library of common pathologies. For each pathology in the library relevant to the rule's domain, the auditor designs a break test. This test varies a specific, supposedly irrelevant pipeline parameter and checks if the rule's core omega KV relationship collapses. Let us formalize a pathology test. Let P be a pipeline parameter suspected of inducing an artifact. For example, filter cutoff frequency omega C, grid spacing delta X, choice of reference frame. The rule G is inferred with the pipeline set to its default value P0. The pathology test involves 1. Varying P over a reasonable range that still produces valid data. For example, different filter bandwidths that don't obliterate the signal. 2. Reinferring the rule's parameters theta p for each value. 3. Computing the sensitivity. S is equal to d theta dp, the rate of change of the rule's parameters with the pipeline parameter. If S is large, if the rule's parameters change dramatically with changes to P, then the rule is pathologically dependent on P. Its success was contingent on that specific pipeline setting. If S is small, within the natural statistical uncertainty of theta, the rule is robust to that potential pathology. The firewall's library contains known pathologies: aliasing artifacts, Gibbs phenomena, frame-dependent forces, overfitting, general, data leakage, where information from the future or outside contaminates training, and omega pathology, batch effects, K pathology from instrument calibration groups. Let us state with crystalline clarity what is allowed and what is forbidden at this gate. What is allowed? You are allowed to use sophisticated pipelines with many parameters. You are allowed to discover rules that work well. However, before a rule can be licensed, you must run it through a set of standard pathology detectors relevant to its domain. You must demonstrate that the rule's success is not critically sensitive to pipeline parameters that lack a direct physical interpretation in phi. What is forbidden? You may not claim a discovery without having tested for known pathologies in your field. Hide or dismiss sensitivity to pipeline parameters as a technical detail. Argue that because a rule works on one dataset with one pipeline, it is necessarily true. Use a pipeline so complex and opaque that pathology detection is impossible. This is itself a firewall violation, lack of auditability. What happens when the check fails? The license consequence is corrective and severe. Fail, mark as pathological. Either A, revise inference pipeline and retest from scratch, or B, restrict scope to the pipeline regime if that's the only place it holds. The rule is branded with a pathology flag. Its proponents must either go back to the drawing board and design a new, cleaner pipeline that avoids the artifact, then rediscover the rule from scratch, or if the artifact is inherent to the measurement method, for example, a specific telescope's point spread function, they must narrow the rule scope to explicitly include that pipeline parameter. This rule for galaxy morphology holds for data processed with the Hubble Space Telescope's ACS camera and the X deconvolution algorithm. It becomes a very local, instrumental rule, not the universal law of phi. Now we must state the explicit prediction and falsification for the pathology detector system. Prediction, if the rule is genuine. If a rule is a true constraint on phi, then removing or varying non-physical pre-processing choices should not destroy the omega-kV relationship beyond declared sensitivity. The rule's core parameters should be stable under changes to filter settings, grid resolution, or other non-fundamental pipeline knobs. Falsification condition for the rule's non-pathological nature. If success disappears when you alter a supposedly irrelevant pipeline choice, pathology confirmed. The rule's validity was contingent on that hidden non-physical constraint. It is falsified as a robust law of phi. A canonical example from computational physics is the discovery of vortex crystals in early simulations of 2D turbulence. Simulations using a specific numerical method, spectral methods with a particular dealiasing filter, found beautiful stable patterns of vortices. Rules were proposed for their formation and stability. However, when simulations were run with different numerical methods, finite difference, vortex methods, the vortex crystals often failed to appear or were unstable. The original discovery was a pathology. It depended critically on the numerical method's inherent conservation properties and damping characteristics, K and V artifacts from the discretization and filtering. The rule was not about 2D turbulence phi. It was about a particular numerical phi simulacrum. The pathology detector, comparing different numerical schemes, exposed this. Let us explore an analogy from the intricate and high-stakes process of evaluating the yield of a new wheat variety in the irrigated plains of Kunduz, using a network of agricultural trial plots. The Agricultural Research Institute develops a new high-yield wheat seed, variety Z. They run a season of trials across 50 test plots. Their data processing pipeline is measure harvest weight per plot, correct for soil quality variations using a historical soil map, average the corrected yields, and compare to a control variety. Their rule G is variety Z yields 22% more than the control under standard Kunduz irrigation. The data supports it. The predictions for next season's pilot farms are promising. A skeptical agronomist from a different province, acting as a pathology hunter, reviews their methodology. He consults the Pathology library for agricultural trials. One known pathology is soil correction artifact. If the soil correction model is poorly calibrated or uses outdated maps, it can artificially inflate or deflate yield estimates in a systematic way, creating a spurious variety effect. He designs a pathology test, suspected pipeline parameter P, the soil quality correction model, specifically the weighting function that maps soil map values to yield correction factors. Test. He asks the institute to reanalyze their data using 3 different, equally plausible soil correction models. Their original one, Model A, a simpler model based only on recent soil samples, Model B, and a more complex model incorporating satellite moisture data, Model C. The soil map is a K structure imposed on the data. The correction model is a K processing choice. If the yield advantage of variety Z is genuine, a property of the plant's phi, it should be robust to reasonable changes in this K processing. Results. With Model A, original, plus 22% yield advantage. With Model B, simple recent samples, plus 5% yield advantage. With Model C, complex satellite model, plus 25% yield advantage. The outcome is highly sensitive to the soil correction model. The S value, change in result per change in model, is large. The agronomist identifies a K pathology. The apparent success of variety Z is not robust. It depends critically on a specific, arguably arbitrary, choice in the data processing pipeline. The plus 22% rule is likely an artifact of that specific soil map and correction algorithm. Prediction of a genuine rule failed. The omega K to V relationship, yield as a function of variety corrected for space, is not stable under variation of a non-physical pre-processing choice. Falsification condition met. The success, the 22% figure, disappears under an alternative reasonable pipeline choice, Model B. Pathology confirmed. License consequence. The rule G is marked as pathological. The institute cannot license it as a general agricultural law. They must either A. Revise pipeline and retest. Conduct a new trial where soil quality is measured directly and uniformly in all plots, eliminating the need for a controversial correction model, and then re-estimate the yield advantage from scratch. Extert scope. If they insist their soil model is the official one, they must restrict the rule scope to yield advantage when using the Institute's 2020 soil map and Model A correction. This makes it a rule about their specific assessment method, not about the wheat variety's performance in Kunduz generally. No sensible farmer would adopt it on that basis. In Holophase science, the wheat growth is a phi pattern. The soil correction is a K processing step in the pipeline from field to yield estimate. The pathology detector found that the rule's success was contingent on that processing step, not invariant across reasonable alternatives. It exposed the rule that worked, fit the process data, but was wrong in its claim to be about the plant's intrinsic properties. This discipline is the ultimate refinement of the episode 11 axioms. Rules do not become real by elegance, consensus, or tradition. They earn a license only by surviving falsification, variation, independence, and scope discipline. The pathology detector enforces a higher order variation and independence. It varies the preparatory steps leading to the data, not just the external conditions. It tests for independence from the toolchain, not just from confounders in the world. A rule that cannot survive this is not disciplined. And the cardinal rule: when a rule fails, we do not believe harder. We tighten, downgrade, or retire its license. When pathology is detected, we do not defend the soil model harder. We downgrade the rule to a pipeline-bound artifact, tighten its scope to that pipeline, or retire it and start over with a cleaner method. The skill you gain from this part is causal chain auditing. You learn to trace the success of a rule backward through every step of its creation, asking at each step, is this step injecting a regularity that the rule might be mistakenly attributing to phi? You become an expert in the etiology of error. This skill is what separates masters of a technical field from mere practitioners. This skill has immediate, vital application. In neuroscience, a rule that brain region A activates 300 milliseconds before decision might be a pathology of the specific event-related potential (ERP) averaging technique, which assumes a fixed latency. Varying the alignment method and omega processing choice tests for this. In cosmology, a claimed detection of non-Gaussianity in the CMB might be a pathology of the foreground subtraction pipeline or the map-making algorithm. Changing the component separation method, a KV processing choice, is a standard pathology test. A model's high accuracy might be a pathology of data leakage, where information from the test set inadvertently influences the training process, for example, through prior normalization on the entire dataset. Properly segregating data pre-processing is a pathology detector. In genetics, a gene expression signature for a disease might be a pathology of batch effects. Samples from cases and controls were processed on different days or by different technicians, a KV artifact in the lab. Correcting for batch effects or testing across independent batches is the pathology detector. Finally, let us summarize the epistemic function of this part. Let us crystallize what we have built. We have defined the grammar pathology detector system. This firewall mechanism is a library of diagnostic tests for rules whose apparent success is caused by hidden, non-physical constraints in the data processing pipeline, rather than by true constraints on phi. The firewall acts as a pathology auditor. It subjects successful rules to break tests that vary key pipeline parameters, checking if the rule's omega k v relationships are robust or artifact dependent. The explicit prediction for a genuine rule is pipeline parameter invariance, stability of the rule's core under changes to non-fundamental processing choices. The explicit falsification condition is critical pipeline sensitivity, the collapse of the rule's success when a supposedly irrelevant pipeline parameter is altered, proving the rule is pathological. The license consequence is branding and correction. The rule is flagged as pathological and must either be rederived with a clean pipeline or have its scope severely restricted to the specific pipeline regime. This strengthens the firewall by adding a causality of success check. It ensures that we license only rules whose mechanism of success is the world, not our preparation of the world. It is the final guard against the clever, self-reinforcing artifact that can fool all other tests. With pathology detection, the firewall's diagnostic arsenal is complete. It can now detect failures of measurement, inference, causality, scope, and now the very genesis of success. Yet, there is a final structural vulnerability. Rules are not isolated. They are inferred in chains. One weak link, one pathological assumption or unvalidated intermediate rule can collapse the entire inferential structure that follows. This leads us to the final component: inferential chain validation. Salam, and peace be upon you.